So welcome everyone. Welcome back to Math 211. We are now on Thursday of week 12. So it's probably the 24th lecture. Definitely it's November 18th, but I don't remember if we missed any lectures or not. But we are currently working on chapter 19, sampling methods and sampling distributions. We last time talked about the difference between samples and the population from which the sample comes, sample size, sample error. We had some examples. We did some methods of sampling and talked about various ways of sampling that are good versus bad. Random sampling is the best. And we're gonna skin, and we definitely did this one here. So, oh, I remember that one. Okay, so let's start on page. Let's start here on page 16. Sampling distributions are a California Common Core topic for 7th grade. And what is the objective? Use data from a random sample to draw inferences about a population with an unknown characteristic of interest. Maybe you don't know the average, maybe you don't know the proportion, whatever the case may be. Generate multiple samples, or if you go back all the way to, I think, chapter 2, simulated samples of the same size to gauge the variation in estimates or prediction. So for example, let's just suppose, and I've used this example like 1,000 times, but let's suppose I'm interested in the average height of a CSUN student. There's some 40,000 CSUN students. So perhaps I went ahead and I took a sample of size 100 and I computed the average from my sample. So first question, do I expect that the average of my sample to be the true value for the average of all CSUN students? Whatever the true value is, do I expect that my sample average should match that perfectly?
No.
Probably not. I mean, I could, of course, get coincidentally lucky, but for the most part, a random sample will probably not give me the true value. Now, if I took lots and lots of samples of size 100, would I expect that they would all have the same value? If I took a sample of size 100, got the average, another sample of size 100, got the average, another sample of size 100, got the average. If I took lots and lots of samples of size 100, would I expect them all to agree on the value that they get?
No.
I'd be very shocked if they did. I would imagine lots of repeats if I had lots and lots of samples, but they shouldn't all be the same, which means that if I plotted all of my sample values, I would probably get a dot plot or a histogram, depending on what kind of visual display I want to use. But I would get a display of some kind that itself has an average and it has some spread. It has some variance, some standard deviation. And I want to use my sample distribution to infer properties of the original distribution. For example, I know from statistical theory, and I think intuitively, that if you averaged all of your averages, again, we're averaging averages here. So we take lots and lots of samples of size 100, and we get lots and lots of values, and we average those values. That would probably be somewhere in the vicinity of the true value we would expect. So if I went ahead and took lots and lots of samples of size 40. Okay, so I took Skittles. I went to Skittles R Us. I went to the Skittles factory, and they have, presumably, I'm guessing here, but they probably have somewhere in their manufacturing process, they've manufactured all of their Skittles, and now they're all being mixed in some huge vat. and then, something pours Skittles into packages, which they seal up and ship out. So perhaps I went ahead and I took 40 Skittles at a time from this huge vat of all of their Skittles. And I took all of my samples and computed all of the proportions of reds in all of those things. I might get a dot plot that looks something like this. Lots of times, I'm going to have 20% of my sample to be red. And not pretty often, but not quite as often, I'm going to have either 18% or 22%, 15, 60, whatever numbers these are. I think they're off a little bit. But, or not necessarily, because out of 40, it's not a perfect number. But does it make sense that most of the time I would have something in the vicinity of 20%, which is the true value, and very, very, very infrequently would I have values that are far away from 20%? Does that seem reasonable? Is everyone following this scenario that is occurring here?
Yes.
Yeah.
Okay, so this seems reasonable. This seems reasonable. You take 40 at a time. We know the true value is 20%. So usually it'll be somewhere in the vicinity of 20%. And if I got no reds or one red or two reds or 38 reds, I'd be like, whoa, that's so unlikely to happen. Of course, if I took thousands upon thousands upon thousands of samples, it might happen a couple times, but it's still pretty unlikely. So you'd have a distribution that looks like this. Its peak, its center, its balance point is at 20%, which seems very reasonable because the true value is 20%. And its spread is pretty far across the page. It's got all the way to 5% here and 37% here. So it's got some spread. If I, instead of taking 40 at a time, took 1,000 at a time, would I expect in 1,000 Skittles at a time to get just a few reds? Does it seem reasonable that for 1,000 Skittles, I'd have 5% reds and 1,000?
No.
It's a lot less likely to have a value of 5% with a sample that big, because the bigger the sample, the more likely I am to be close to the true value. And in fact, if I make a distribution of 1,000 at a time, then notice that we get a one that looks like this. It's still centered at 20%, but what do you notice about the variance, about the spread of possible values in the case of 40 at a time versus 1,000 at a time? What do you notice happens?
It's closer to the true value.
It's much closer to the true. The spread has shrunk considerably, much closer to the true value. Okay, this is the idea. Again, if you recall back in the very beginning of the course, we had, remember that idea of stabilization and the law of large numbers? I think it might have been chapter 1. Do you guys recall that?
Yeah.
In the very beginning, that the more samples, the more trials you take, the more likely you are to stabilize to the true value. It's the same principle here. If I have 40 at a time, there's a lot of wiggle room. I haven't reached stabilization yet. I can be all over the place. But with 1,000 at a time, it's much less likely to be far away from the true value. So P hat, my sample proportion, we know P is actually 20%. That's the true value. P hat is my sample proportion. That is much closer, much more condensed and clustered around 20% than the original one was. Does that make sense? So hopefully it does. Okay. In this example, if I want a interval, if I want to go left and right to the center, that contains 95% of my data points, 95% of my dots, how far do I need to go left and right from the center to get 95% of my data points, approximately at least?
I would say from like 0.12 to 0.28.
Okay, so you're suggesting whether this is, it's certainly ballpark, that you're saying that this, oh, 28, you said, 1 second. So you said this is about 95% of my data? Yes?
Yeah, I think.
Well, there's not that many dots, so let's actually see if that's correct. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 and 13, that's 23, 33, 43, 56, 57, 58, 59, 60, 61, 71, 2, 3, 4, 5, 6, 7, 8, 9. That's 80. And that leaves 5, 2, 2, 4, and 3, 4, 5, 6, 7. So that's 7, 11, 13, 14, 15, 20. Well, there's exactly 100 of that. Wow, look at that, 100 different samples. Woo, that was a waste of time. So to get 95%, we'd actually have to go further. I'd have to go almost to about there to get 95%. Agreed?
Yeah.
Yeah, I mean, even then, I actually got 96%, but ballpark. So it looks like from here to here is how far I'd have to go left and right to get 95% of my data points. Whereas in this case here, if I want 95% of my data points, how far do I got to go now? How far from 20% do I go left and right to get 95% of my data points? It looks
From
like
0.18 to
A
0.22.
little bit after 0.22. Yeah.
something like that, right? Give or take. That's a lot smaller of a spread to get 95% in the case of 1,000 at a time than it is to get 40 at a time, correct?
Yeah.
So the sampling distribution of reds is centered at 0.20, no matter how many skittles are in each sample. Either way, it's going to be centered at 0.2. However, with a larger sample size, the variability gets smaller. And the shape gets, I guess, tighter is a better word. I don't know. Shape gets, it's more condensed. If we select 40 at a time, you have about a 95% chance of getting between, what were those numbers we gave? About 9% and 34%. So in the case of 40, it was about 95, it was between 9% and what did I just say? Crap. Anyone?
34.
34, 9 and 34. Whereas in the case of 1,000 at a time, if I wanted 95%, how far would I have to go? To about 17% and 22%, something like that. Ballpark, yes?
Yeah.
All right, so it's much, oh, I was redundant. I wrote percent. That's the right stuff. So again, what do we see? We see that for the larger sample size, to get 95% of them, you don't go nearly as far. And this illustrates why, which one of these are better, smaller samples or bigger samples? Smaller or larger? Which one's better? Smaller samples or larger? samples? Huh?
Larger.
Larger for sure. Larger samples are much better. So let's take a look at this one. Despite knowing how dangerous it is, and despite the laws against it, 3/4 of drivers who own cell phones admit to texting while driving. Naughty. Now, if 75% admit to texting while driving, do you think the true value is smaller, the same, or bigger than that value?
Bigger.
Why would it be bigger? You
I
suggesting
think some people wouldn't admit it.
people wouldn't admit it. Let's take a look at this class. Who here texts while driving?
I'm still learning how to drive, so I don't do.
So look at that. Statistically, we got some liars here. Terrible as it is, I do. We have one person being honest. Well, I'll lead the pack. I certainly do. I am a horrible person. I learned how to drive before seatbelts were a thing. So exactly, Harmony, right? Once it became illegal after already driving, it's like, I didn't do this. Yeah. So okay, did you get that, guys? All right, we got some people who admitted it. Okay, good. All right. So if the police come to any of you, it wasn't my fault, I promise. It's like, but I'm good at it. Right. That's what we all feel, right? It's like, yeah, they should be doing it, but I'm pretty good at this thing. I can do it. So I mean, I've been driving for almost 30 years. Now, I haven't been texting that long because phones weren't a thing. I mean, cell phones weren't a thing. When did cell phones come out? When do we have cell phones? How long has it been?
90s?
Is it the 90s? It's been that long? Jeez, time flies. Oh, yeah.
Yeah.
I feel old. Late 90s. Okay, so 20 something years. I'm with you, Harmony. Like, I'm good at it. You know, I can keep my eyes on the road and text at the same time. Like, you know, not, oh shit. We're on I'm recording this. Okay, wow.
Doing on YouTube. Don't
It's a
forget.
hypothetical situation. It's not real.
This is a statistical example, right? We're just kind of saying it's a social experiment. Nothing we say here actually is true, including
It is part of the problem of, for the group lesson.
This is
It's
a
all
story.
learning
This is all
experiment.
made up. We're making a scene here. So-
right. Okay, let's just keep going. But Harmony, oh, that's pretty cool. I know the keyboard so well, my eyes never leave the road. I wish I could do that. So you're actually justifying it. I love it. This is we're playing pretend. That's all that matters. But I'm with you, Harmony. I will readily admit, even online, I will readily admit that I'm not perfect when it comes to this. But anyways, suppose you take a sample of 50 drivers who own cell phones and ask them if they ever text while driving, and 42 of them said yes. So what is N in this example? The letter N that we've been using for this chapter. What is the value of N in this example?
50.
50. N is the sample size. We asked 50 people, and that is the size of my sample. What is P hat in this example? And what is P in this example? Either one of them. What is P and what is P hat? Anyone know? P and P hat.
Well, P would be 42, right?
No, P would not be 42. P is a proportion and P hat is a proportion. Proportions have to be between 0% and 100%, or between 0 and 1. And 42, unfortunately, is way too big to be a proportion. So first, conceptually, what's P and what's P hat? Forget about the actual numbers. What is P and P hat conceptually? Yeah.
The true value and
And
the, I forget the word.
the sample value. P is the true proportion of drivers who text while driving. What is that value? What is the true proportion of drivers who text while driving?
0.84 then?
0.84 is not the true proportion. 0.84 is the proportion of my sample. 42 out of 50 is 84%. That's my sample proportion. What's the true proportion based upon the words written on this page?
3/4.
3/4 or 0.75. 3/4 of drivers who own cell phones admits to texting while driving. 84% of my sample has admitted to texting while driving. So the true proportion is 75%. Now you might ask, well, how do they know the true proportion? And the answer to that is, well, they took a sample. But we're assuming for the sake of this discussion that that's the true value. So now circle the sampling distribution for this situation. In other words, if I took lots and lots and lots and lots and lots of samples of size 50, and I made a histogram of the results of the percentages of people who admit while texting, which one of those three is the most likely scenario for that distribution? The left, the middle, or the right? And of course, why?
Would it be the right because the true value is in the middle?
So you mean the far right, the third, this one here?
Yeah. Yeah.
So when you say the middle, do you mean the halfway through the graph? Because that's the middle. So what do you mean by middle here?
Well, because the arrow is pointing to the 0.75, which is the true value.
So if we want it to be centered to the true value. This one is out because it's not centered at the true value. But this one seems that it could be centered at the true value as well. Right? That's a little bit to the left of 0.8, right?
Yeah.
So how do I know if it's this one or if it's this one? So remember, we're doing samples of size 40, correct? They only took a sample of size 50. Every sample is size 50. That's correct. No other size samples at all, just 50. So if I took a sample of size 50 and I got 75% who said they text while driving, how many is that? What is 75% of 50?
%75 of 50 is 37.5.
So this is the one for 37.5 people. Good luck finding that. This is the one for 50 out of 50. This is the one for 25 out of 50. This is the one for 12.5 out of 50. And this is the one for 0 out of 50. So even if you say, okay, what I really meant is like right around 37.5. What about 26 or 27 or 28 or 29 or 30, 31? What about all the other ones in the middle? Are those not possible? Do we not get them? Do that seem reasonable? That we should have a scenario like that? Or should we have a scenario where each value is possible, but the further you get from the true value, the less likely it is. So it kind of tapers off on both sides. Which one of those seems more reasonable?
Yeah, the first one.
The first one. Why did you select the one you did? Because it's the right one. It's a good question. Okay. Example. This graph shows the number of children per family in the United States. For example, about 20% of families have one child. And the average number of children per family is 1.1. More than half of families have no children. That's either a contrived example or surprising. But it is what it is. So if these graphs show sampling distributions of the mean number of children for random samples of US families of size 4, of size 10, and of size 40. Which do you think is which? Which of these three do you think is size 4, 10, and 40? What I want everyone to do, wait for me to call and say go. But when I go, I would like in chat you to put three numbers in order. The one on the left, the one in the middle, and the one on the right, which number you think is which. So for example, if I think it's 4 on the left and 10 in the middle and 40 on the right, I would put in 4, 10, 40 in that order. The three numbers are left, middle, right. And I would like everyone to type it in the chat, and I'll give you a couple seconds to think about it. And then I'll say go. And when I say go, I would like everyone to type it in. Okay, so 3, 2, 1, go. So that's 11 people. So I think my definition of everyone and yours might not exactly be the same. Still missing some people, but at this point, we got peer pressure possibly. So when I look at the answers, everyone's answers, I see that just about everyone, but not everyone, but just about everyone correctly said that this one here in the middle was 40. Just about everyone said that. And because why? Because the bigger the sample, the tighter the curve. And this one is certainly the tightest of the three. And then this is the widest of the three. And then this is somewhere in between. So it should be 10, 44, which was not everyone, but it was just about everyone, just about everyone. Does that make sense though? I mean, they're all centered at 1.1, approximately at least. And therefore it's the spread that distinguishes them. In fact, if you look at this one, yeah, 1.1, not the peak, but there's a right tail, so it's skewed to the right. So it's a little bit to the right. 1.1 seems reasonable. Here, 1.1, pretty close. 1.1, pretty close. Yeah, it's all about the spread. Does that make sense?
Yep.
All right. And that takes us to the end of chapter 19. How nice was that? As the sample size increases, the sampling distribution of the mean gets tighter in shape or smaller in shape. The mean stays the same while the variability decreases. Does that make sense? Yes,
Yeah.
no, no? Any questions on this chapter? All right, well, then it's time to move on to chapter 20. And this is one of the two main concepts and the main objectives of statistics is testing statistical significance. Essentially, here's the idea. You do an experiment and you get a result. And from that result, you'd like to make a conclusion. For example, maybe maybe I'm a wood carver, my hobby, and I have crafted a coin that I claim is fair. And I would like to use this coin to do, games of chance Super Bowl decisions of who goes first and so on. So the question is the coin fair? How do I determine if my coin is fair or not? What can I do to determine if my coin is fair? I mean, you can't just take my word for it.
You can flip it a certain amount of times and try to find the probability.
Okay, so I can flip it lots and lots and lots of times. Let's say I flip it 1,000 times. If it was fair, if it was truly fair, how many heads and how many tails would I get if I flip it 1,000 times?
Should be roughly half and half.
Should be roughly half and half. So if I got 500, 500, or 510, 490, or something in that vicinity, would you have any evidence to suggest that it wasn't fair?
No,
No. What if I flipped it 1,000 times and I got 900 heads and 100 tails? Would you
that
have
would be a problem.
That might be a problem. Okay, that's far enough away that you're like, well, wait a second. I don't really think that this result would happen if it really was a fair coin. So when you get a result that is unlikely to have occurred by chance, we say that it's a statistically significant result. It might not be practically significant. It turns out in the case of the coin, it really doesn't matter if it's fair or not. Because at the end of the day, as long as you don't know which side is more likely, then the odds of getting it for your side is the same, whether it's fair or not. You can actually prove that mathematically. Pretty cool. If you go into a coin toss and you don't know which side is more likely, so you're going to call either side purely randomly, then the chance that you are correct is still going to be 50%. And therefore, while there might be a statistically significant result that my coin is not fair, I don't have any practical significance that the coin is not fair. Who cares? Just move on. So this is the idea of statistical significance. And of course, we want to make it very mathematical so that everyone agrees. You said 900, we're going to reject. We're going to say, oh, the coin's not fair. But 510, the coin is fair, or at least it might be fair. So somewhere between a 510 and 900 is going to be that balance point where we shift from not fair to fair. Where is that point?
Begin lockdown drill.
I have a lockdown drill now, so I'm just going to stay in this room. Okay, so chapter 20, testing statistical significance. To test whether she could recognize herself in a mirror, an X was placed on the forehead of Happy, a 34-year-old Asian elephant at the Bronx Zoo. It's more like a cheek, not a forehead, but anyways. After observing the mark in the mirror on 12 occasions, but not before, Happy used her trunk to touch the mark. She never touched the other side of her forehead, which had been given a transparent X. Say what? After observing the mark in the mirror on 12 occasions, but not before, Happy used her trunk to touch the mark. She never touched the other side of her forehead, which had been given a transparent X. If Happy touches one side of her forehead at random 12 different times. Okay, so I'm not quite getting what they're saying, but I'm going to change it just to make it make sense in my head. Suppose as an elephant, you randomly touch a part of your face. If you don't know that you're looking at yourself, if you just touch randomly 12 times, then how many times would you expect to touch each side of your face?
6.
6 each, right? That's what you would expect if there was no reason to do more in one side than the other. Now, if I recognize myself in the mirror and I see something over here, I'm like, oh, what is that? I might, scrape it off or do something like that. And I would be more inclined to touch that side of my face more often. Does that seem reasonable?
Yes.
Okay. So, it says, okay, so it says that all 12 times Happy touched that side of her face. She never touched the other side of her forehead. So all 12 times the elephant touched the side of her face that had the mark. All 12 times. Now, if it was completely at random, it should have been 6 and 6. This was 12 and 0. What do you conclude about your study? Was the elephant able to recognize herself, or did she just get really, really lucky?
I think she recognized herself.
Okay, so I think she recognized herself too. We have to ask ourselves, what's the likelihood that you randomly touch one side 12 times in a row if it should be perfectly random versus, oh, wait, there's a reason behind why you're doing what you're doing. So in this case, if you do it all 12 times, that's probably an indication that she recognizes herself. If it was 100 times, I think we would all agree. 12 times, maybe it's too close to the true value, maybe not. Let's try to do another example, which is a little more obvious. Chernobyl. You guys all familiar with Chernobyl? The 1986 accident at the Chernobyl nuclear reactor. This was before, before your time, but I was around when it happened, 1986. So there was a nuclear accident, and it brought about concern that the radiation might cause mutations in the genes of humans and animals that would be passed on to offspring. Before the accident, 2% of barn swallows had white feathers in places where the plumage is normally blue or red. Why in general do they have white? That's a genetic mutation. That's just the way the universe is. Now, in a sample of 266 barn swallows captured around Chernobyl between 1991 and 2000, 16% had white feathers in places where the plumage is normally blue or red. You will learn in this chapter to decide whether the evidence that the rate of mutations was higher in Chernobyl after the accident is statistically significant, or it could have happened by chance. There's a reasonable chance that it could have occurred on its own. It's a 14% difference. 14%, maybe that's pretty far away, that the result makes me think, okay, there's a reason behind this. Or maybe it's close enough that I think, hey, we live in an imperfect world. Sometimes we get results that are unexpected, but hey, that's just the way life is. We have to be able to distinguish between statistically significant results that are extremely unlikely to have occurred by chance alone, versus results that might be unlikely, but can be attributed to chance. Does that make sense? The goal of this chapter? Everyone? What we're trying to do here?
Yeah.
Makes sense to me. Yep.
Okay. So, and a couple people chatted, so hopefully they said yes. Oh, one was a yes, and one was a yes. I love that. Okay, so unless that was an n factorial, that would just make no sense, but I'm going to go with yes. Okay, so fill in the values that correspond to each symbol. N is the sample size. In this example, what is the sample size? How many barn swallows am I looking at in my sample?
266.
266. Okay. P hats. The proportion of yeses in the sample, the proportion of the successes, the proportion of whatever it is that I'm looking for in my sample. What proportion of my sample were yeses?
lockdown drill has edited. Thank you, everyone.
What is the proportion of yeses in my sample? %16. 16% had white feathers in places where the plumage is normally blue or red. Now, I actually looked at 16% of 266 and it was not a whole number. 16% of 266 would be 42.5. So I looked at 43 and 42. So the actual number of yeses in the sample, it's impossible to know for certain, but it's either 43 or 42 because 44 out of 266 would have rounded to 17%, and 41 out of 266 would have rounded to 15%. So the only two numbers that would have rounded to 16% are 43 and 42, but it's impossible to know the exact value. So 43 is a little bit closer to 16%. We're going to say 43. Now, what is the standard against which the sample is to be compared? Our sample value is 16% or 16.16541353%. What are we comparing it to? What's the value that we're testing to see? Is it the same? Is it not the same? Is it bigger? Is it smaller? What value are we comparing it to?
The 2%.
The 2%. That's what it's been until now. That's where it is everywhere else in the world. We're questioning, did Chernobyl make it more than 2%? Or is it still 2%? So 2% is the standard against which we're comparing it to. Make sense?
Yep.
Okay, now, if this was a class a little higher in statistics, I would go directly to my calculator and I would plug in, I would go to my stat test and I know exactly what type of test that we're doing here. I'm just going to do it very quick to see what the result is. What do we say? 43 of them of the 266. And what I see here is that this is a extremely significant result. That if it was really 2%, 16% would essentially never happen. Do you know what the value is for 60? The likelihood of getting the 16% is 1.87 times 10 to the negative 61 power. Negative 61 power. That's essentially 59 or 58 zeros, 0.00000, 58 zeros, and then 187 or something like that. 60 zeros, whatever it is. That's how likely it is. So this is an extremely statistically significant result. But in this class, we don't do that. We do it in a different way. We do it graphically and we kind of get an idea. So let's look through a few examples. What we have here is a 266 sample size, n equals 266, true value 2%. Notice that, what is, by the way, 2% of 266? I'm curious. What is 2% of 266? Anyone? What's 1% of 266?
2% is 5.32.
5.32. Does this look like we're centered at 5.32? Does that seem like a reasonable value?
Yes.
Okay, so this is 5.32. And this is the likelihood of getting every result from 0 to technically infinity. It goes on forever, or not infinity, 266, right? You can have 0 of them have it. You can have 1 of them have it. You can have 2 of them have it, 5 of them, 6 of them, 7, and so on. So we're claiming that 43 of them had it. Where is 43 on this graph? Here's 0, here's 1, here's 2, here's 3. Where's 43 on this graph? Anyone see 43? Where would 43 be located? '43 is all the way off the graph that way. way down. 0 to 14, so 28, 42. Basically, 3 more graphs down, you'd find 43. What do you think the probability of getting 43 is if we continue this the way it's been going? How likely is it to get 43? Imagine mentally continuing this graph as it tapers off. How likely is it to get a result of 43? Highly unlikely, likely, somewhat likely,
Highly
Highly
unlikely.
highly unlikely. So if you actually did get 43, would you say, yeah, I think P is 2%. That's a possible outcome. Or would you say, yeah, chances are P wasn't really 2% after all? Which of those is the more likely conclusion to make? Psst, this is for everyone. That it wasn't 2%. This is the idea of a statistical test. You look at the result, you look at how likely the outcome was if what you believe to be true was actually true. And then from that, you decide whether or not you're going to go with it. So this is a sampling distribution for this situation of picking 266 at a time. What was the size of each sample in this particular distribution? Every one of them was 266. Every single one of them was size 266. What value of P was used to construct it? 5.32. Sorry, not P. P was a 0.02. What does the bar above 4 represent? What does this bar here represent? This one right here. What is that bar?
17.
Well, 7.17 what? But what does that mean, 0.17? That's a number, but what does it tell you?
The probability of it occurring.
What's the it's that's occurring? That's why I'm trying to nail down exactly what we're talking about and not just use loose numbers, but rather really concretely suggest what it is.
The probability that 4 birds have white feathers.
So the probability, it's not so much the probability. It's, even though I know it says it on the left, it's more of all of my samples, 17% approximately of those samples ended up with 4 birds having white feathers or white plumage, whatever. What the hell is plumage anyways? Is that feathers?
I have no idea.
I don't know either. We'll say feathers because I don't know what the word plumage means. I'm not even sure I'm pronouncing it right. So 17% of the feathers that come off.
So 17% of the 266.
No, 17% of my samples. Not 17% of 266. It's 4 of 266. I took lots and lots of samples. 17% of my samples had 4 birds with white feathers that come off, according to Harmony. How many of my samples had 5 birds like that?
Like 18%.
Like 18%. What percent have 43 birds like that?
Wouldn't that be like a very low number, like 0.00?
Yeah, it's essentially never going to happen. It's essentially never going to happen. So because that's the result that I got from my real sample that I actually took, it really makes me question the fact that 2% is correct. So what's the mean of the distribution? The mean of the distribution looks like to be 5.3 or so. 5.3. So question. Same situation, same graph, just it's a little smaller this time, but it's the same graph. Actually, same size, looks like. What is the largest number of birds with white feathers that it's possible to get in a sample of size 266? If I take a sample of size 266 and I count the number of birds that have white feathers, what is the largest possible number that I can conceivably get in the universe? How many of those 266 could possibly have white feathers?
Based on the graph or just
Well, just based upon possibilities.
266?
Yeah, in theory, all of them could have white feathers. However, what's the largest number that it's plausible to get? That if you got it, you wouldn't start questioning the very nature of existence. This does come from the graph. What's the largest number where you would say, yeah, okay, I can see that happening.
The 13?
Well, that's the largest number, but even this 13 is what, 1%? Maybe 0.5%? Right?
Maybe 8 or 9.
Well, 8 is around 7%. 9 is about 5%. What's the cutoff? What's the point at which you say that percent is just too low for me to think it's plausible? What's the cutoff percent? 1%? 2, 10, 100? What's the cutoff?
I would say like the 0.7, 0.5-ish.
0.5 is 50%.
I mean 0.05.
Okay, so it's normally considered that anything less than 5% is not really considered plausible. That's a general cutoff in statistics, which means around 9 or 10, maybe 9, is really the largest amount that I would say that it's plausible to get. Again, you still have like a 2% chance of getting 10 and a 1% chance of getting an 11. It's certainly, if I take lots and lots and lots of samples, I'll have that 1% chance occur now and again. Correct?
Yeah.
Okay, but the boundary between plausibility and non-plausibility is usually taken to be 5%. So place an X where the results from an actual sample be located right here. This is basically the cutoff. Anything past that, and I'm like, I'm going to start questioning whether 2% was really correct. Now, what approximately is the probability of getting 43 or even more than 43? And the answer is essentially 0. There's so little chance of it happening that, yeah, go ahead.
For the like 0.05 cutoff, would that also go for the other side too, or only for the 9?
No, both sides.
Okay.
Both sides. So basically any results from 2 to 9, I wouldn't take my results and say, 2%, yeah, I don't see it happening. But anything past 2 or past 9, and I would certainly question the validity of 2%. That's the idea. And in fact, the p-value, which is an extremely important concept in statistics, the p-value is the probability of getting what you actually got or anything past it, or even more, if this was really true. The p-value is the likelihood of getting what you got or something even past it if your underlying assumptions are valid. So I was tutoring someone a couple weeks ago and they had the following statement. And I kind of liked it. It said, if the p-value is low, if the p-value is low, the null, which is your original assumption, the null must what? What do you think the conclusion was? If the p-value is low, the null, your original assumption, must? Anyone?
Be incorrect.
Well, that doesn't rhyme at all. Jeez. If the p-value is low, the null must
Go.
go. If the p-value is low, the null must go. If the p-value is high, let the null
Rise.
wow, you guys, your powers of rhyming are amazing. Rise. If the p-value is low,
I said rise.
It's not rise. It's not, doesn't rhyme.
Fly.
Let the null fly.
Rise rhymes what?
How does rise rhyme with high? You're high. Okay. If the p-value is high, let the null fly. I kind of like that expression. Never heard it before last week, and I've been teaching this up for years. If the p-value is low, the null must go. If the p-value is high, let the null fly. Rise. This doesn't even make sense. Anyways, so let's understand what that means. Small p-values are very unlikely results. Very unlikely results make me question my underlying assumptions. The null hypothesis is what it's called. Low p-values are unlikely results if the null is true. So the null is more than likely not true. I'm going to let the null go. High p-values means it's somewhat likely that I would have gotten that result if the null was true. If it's a likely result that the null is true, why would I question the null? I'm going to let it fly. It might not be right, but my evidence doesn't tell me that. Does that make sense? The idea? Yes,
Yeah.
no, maybe so. Okay, so the p-value is the probability of getting a result from a random sample as extreme or even more extreme than the one from the actual sample. If the p-value is small, typically less than 5%, it's quite unlikely to get such a sample. Thus, the result of the study is said to be statistically significant. It's a low probability of having occurred by chance alone. So you want to look at it and understand why it occurred. Did it occur because your underlying assumptions were wrong and therefore you want to change them? Or possibly for some other reason? In the case of the Chernobyl study, was it statistically significant or was it not statistically significant? My 16% result. Could it be attributed to chance alone, or was it statistically significant?
It was statistically significant.
It was certainly statistically significant. We saw that the chance of it occurring is essentially 0. 10 to the negative 61 power. Okay. So does the study provide convincing evidence that there was a higher rate of these mutations in the barn swallows around Chernobyl after the accident than before? The answer is yes. And does that mean Chernobyl caused it? That's a whole nother question. That's something beyond statistics. Statistics just says, yes, it's higher now than it was before. The why, I'll leave that up to you. So we will stop here and we'll continue this on Tuesday. And we need to have a quiz sometime. So what's a good chapter to have the quiz on? We're on chapter 20 now. So what's a good chapter to have a quiz on?
Nineteen.
On sampling distributions, that's what you want? 19? Okay. Well, no one else is talking, so 19 it
No,
is.
no, wait.
Wow, I give you opportunity. What do you want to say?
Hold on, because let me look at the homeworks.
Okay.
Sorry. Yeah, 1 minute.
Or 17, since the review already for the answers of the questions already done for homework.
Okay. Well, also, I'll put up the other stuff. Well, 19, we finished. No, we finished it today, so. I haven't put up the solutions for 19 yet. But we still have like 3 weeks for 2 more quizzes. We'll figure it out. Maybe 17. We'll see. Okay, either way, I will let you know if I put it up. So I gotta go to my next class. Everyone, have a great weekend, and I'll see you on Tuesday.
Bye.
Get those orange creamsicles, damn it.
I will try my best.